Welcome back, guys and gal. I read the statistics. I know she's here somewhere. In the last video, we calculated my engine static compression ratio, and in this video, we're doing something completely different. But all of the tools I showed are exactly the same. There's a few extra tools that I don't have here on the workbench, and it's because we haven't made them yet. I showed a pair of 1-pound test springs used to check valve clearance, but there's a more important measurement that we need to take first. The tool that nobody guessed from the last video was a degree wheel. We're going to put the head on the block today, degree the cams, and check the valve clearance, but first we need to install those test springs. I'm installing them on the front two lifters, which really aren't the best ones on which to do this. The oil galleries make it a bit cramped for the measurements we'll be taking, but I'm proving that it can be done. Once you've got the valve spring, or in my case, the valve springs out of the way, it's easy to install the test spring. These are lightweight 1-pound springs picked up from the local hardware store. If you can't install these by hand, you seriously need to start working out. The reason I'm concerned enough to degree the cams and check the valve clearance is because I've gone far beyond the factory service limits on the deck surfaces of both the block and the head. I'm not taking any chances with the changes that I've made. But this is always a good thing to check anyways, because there's no guarantee that even the factory parts will meet the engineered specifications. Aside from resurfacing the deck, other variables play into valve clearance and valve timing. Camshafts are usually not identical to their engineered specs. Variations in forging and cam grinding cause anomalies in the engineer's specifications, just like how the dowel pin locations may not be perfect or the keyway on the crank may be slightly off center. All of these kinds of conditions will throw off the timing of the valve opening and closing events relative to the crankshaft. A 4G63 is somewhat forgiving though. When you use stock unmachined, unmolested components and follow your timing marks, it's pretty easy to get it right. But aggressive cam profiles and heavily machined parts may result in inadequate valve clearance with the pistons. After you've got your test springs installed, it's time to start putting things together. Start by installing your dowel pins. New ones are always best. You can get away with reusing them if the head and the block don't change, but I always replace them. Once you have the dowel pins in place, it's easy to align your head gasket. Then after wiping down the head's deck surface, the head gets installed. Look through the bolt holes on the corner of the cylinder head at the dowel pins as you lower the head onto the block. Next, install your head bolt washers and head bolts. You want to use clean engine oil on all of the threads if you're using factory bolts. That's what the torque specifications are based on. If you change to any aftermarket or non-standard fasteners, then follow the lubrication and torque recommendations for the fasteners that you're using. But we can go ahead and forget about those torque specs for right now because we just want to use the proper thread lubricant. I'm not going to fully torque and crush my head gasket just yet. We'll have to remove the test springs once we're done and install the right valve springs, so I'll be pulling the head right back off after this. If the head gasket's crushed and then disturbed, there's an infinitely greater chance that it may leak after it's retorqued. We just want to hand snug all of these bolts so that the head and the gasket both sit flush against the block. We'll work the difference between the crushed and uncrushed head gasket thicknesses into our math today. Let's go back to that degree wheel. This is the $20 Summit Racing 11-inch degree wheel. It comes with only what you see here. It comes with a wheel and a set of collets for different sized bolts. The rest of what we need we have to make. The degree wheel has 6 holes around the center which allow you to adapt it to many popular engine choices, and it'll bolt down to an ATI dampener pulley, but we don't have that, and they don't line up anywhere on a 4G63 or any of the factory components. There are no external threaded holes on a DSM crank pulley that let you bolt this thing down, and the center bolt is recessed inside the damper so that you can't even use the center bolt hole. Even if you could do it by removing the crank pulley, what you'll quickly discover is that the degree wheel won't clear many of the other obstacles on the front of the engine, like the water pump and the timing mounts. So it's impossible to use this tool unless you take measures to adapt to these challenges. Everyone who does this does it a little bit differently, but I'm going to show you how I'm going to deal with it. I've got a few old crank timing gear bolts lying around looking for a job, as well as a 1/2-inch drive 22mm impact socket from an old broken up set that I decommissioned. My goal here is to make both of these things one piece. I discovered something cool about this old Harbor Freight 22mm socket. The hole in it. If you ever need to make an M12 threaded hole, the pilot bit for those threads is a 7/16 inch or an 11mm. 7/16 is really 0.2 of a millimeter bigger than it needs to be, which is a tiny amount, but it still gets the job done right. What's cool about this 22mm socket is that it's already got that size hole bored through the center of it. This pre-existing 11mm hole is a convenience that I greatly appreciate not having to drill out myself. Here's a 29/64 inch drill bit. That would be 11.5 millimeters, and it doesn't fit. 7/16 is 11.1 millimeters, so this hole is between 11.1 and 11.5 millimeters in diameter. An M12 tap cuts threads that are 12 millimeters wide, so I've got the meat here that I need to cut these threads. This isn't going to be easy though. I'm expecting to have a casualty. This should be like slicing through a stick of butter using a pat of butter, because both of these tools are made from tool steel. I couldn't find an M12 bolt in my spares that was long enough, but I found an M12 exhaust stud and a lock nut that will work just fine. M12 threads or bust. If I bust, I've still got to put M12 threads in this thing, just to be sure that I'm committed to making this happen, and before I get a chance to change my mind, I'm going to weld the crank pulley bolt to the socket. I have to make this perfectly straight and true to centerline. Any deflection from center will be exaggerated on the other end of the socket. Whenever I had the socket centered and leveled, and the indicator set up on the tip of the bolt, I found that twisting the bolt a little in either direction made it straighten up within a couple of thousandths of center, no matter where I rotated it in the jaws. So while watching the dial indicator to monitor the effects of thermal expansion, I twisted the bolt and tacked it into place on two corners. Then I checked its alignment, making adjustments where necessary. Once satisfied, I set up my dial gauge in a way where I could test the full circumference of the bolt without the need for clamping my work in the vise. I discovered that the entire diameter was within 5/1000ths of an inch, which is perfect because the tip of the dial indicator is narrower than the threads on the bolt. It had the same high and lows no matter which way it was rotated at any angle. We'll see what happens when I install the tool, but I'm happy enough with this to weld the rest of it in place. My welder gave me a fit because I didn't do as much prep work as I should have, but I made it stick. A quick pass on the bench grinder helps to hide my embarrassing welding skills. Now that we've got one step completed, it's time to cut some threads. Keep your fingers crossed. It looks like we made it, but the tap earned a Purple Heart. I'm going to install this thing in just a little bit, but first there are still some more tools that I need to make before this thing will do us any good. I'd like to take a minute to talk about the magnetic bases I'm using here, and you've likely seen these things in several of my other videos doing things from holding my dial gauges to supporting shop lights for close-ups. They have 1,000,001 uses, and this sort of thing is what you'd need at a bare minimum to pull these kinds of tests off. The ones I have here are cheap Harbor Freight junk. I destroyed a few sets of these things because the clamps for the posts are poorly designed. There's a custom machine bolt with half the clamp mechanism built into its head, but it's not really the problem. The problem lies with these lock nuts on the ends of these knobs being slightly larger than the threads on the bolts. Over-tighten them just a little bit too much and they strip the threads right off of these proprietary bolts. If you can't lock these things down, you can't secure the stand, so stripping one of these bolts turns the whole stand into junk. There's another kind of kit available at Harbor Freight that uses a pair of vice grips and a flex stand. I don't have the whole kit here to show you because I gave the included dial gauge to a friend of mine, but that dial gauge has nothing to do with why I'm showing you this kit. The way it works is pretty simple really. You screw the flex stand into one of the holes on the pliers and you clamp it down to something solid. There's a cable going through the center of the flex attachment that has a cam lock. When the cable's loose, you can bend and twist this thing all over the place. But when you turn the cam lock, tension from that cable locks all these little swivel pieces in place, making it rigid. If you can't get it rigid enough, you can tighten or loosen it by turning this collar on the end. Well, that whole flex stand assembly just happens to have the same threads on one end to allow it to screw right down onto one of these magnetic bases. And that's where this tool comes from. It wasn't sold this way. It's two tools turned into one, and I use this thing all the time because it's so convenient. You make a few sacrifices for that convenience. It's not as rigid as a normal stand, but if you get the cable tension right, it's rigid enough that it's not gonna move, and it will still give you accurate readings. There are better tools available that are purpose-built for what we'll be doing today, but this is an acceptable low-cost solution that gets the job done. If you wanted to make one of these, I've showed the item numbers for both kits. No matter how you mount your degree wheel, it won't give you any useful information with the stock lash adjusters, because they compress under load. To accurately measure the cam profiles, you can't let this happen at all. You basically need to convert at least two of your HLAs to solid lift. Solid lifters are available for the 4G63 and with the quality necessary for a running engine, but if you're creative and you have a pile of old parts laying around, you can pretty easily make yourself a set that are adequate for this test. It doesn't really require anything fancy, and you'll see. Another tool I need for this is a thin piece of wire to poke the check valves open with during assembly. Some people use a paper clip. Welding wire works great as well. But you just poke this thing in the lifter holes and they'll purge all the oil trapped below their pistons. We'll get to why that's important later, but that's what this thing's for. With a 1G lifter, this next bit's really easy. You just pop the bottle cap, pull it off the lifter, and pull its guts out. There's still other stuff trapped in by the check valve. We don't need the check valve tool we just made to remove this. In another video, I used fire because I felt like burning stuff. The easiest way to get this out is with an air compressor. You just hit the check valve with the blowgun to launch it out of there, and you'll find the check valve, piston, and spring assembly inside. Depending on how you wish to shim your lifters, you may want to hold on to all these guts. There's a few different ways to build one of these things. Some methods are adjustable and some are non-adjustable. I'm going to make two different kinds from scrap junk just to keep things fresh, but I prefer the adjustable variety. I found this solid flange nut, and I don't even know what it's from, but its outer diameter and rigidity is perfect for this. The M6 threaded hole is also a plus because I have tons of those bolts, and the 10mm nut is a perfect fit inside the bore of this lifter. I'll probably need a longer bolt than this, but I've got tons of these M6 nuts and bolts to trial and error with. All the other nuts I had were either made of materials that I can't weld on, or have this goofy staked on washer thing with no rigidity whatsoever. These things would crush apart in a heartbeat, but I stumbled across an old bit of shifter linkage, and the adjuster screw looks perfect. This piece is also a 10mm hex with M6 threads, giving me the perfect bolt selection here as well. So the convenience is no different for this linkage adjuster thing that I just stumbled across, but at least this won't require any welding. The adjuster isn't long enough, but a couple of spare 10mm nuts underneath it to shim it up to the top gets the job done. In order to make it easier to adjust, I'm just going to cut off and cram a piece of coffee filter in there with it to jam it in place. Accuracy is really unnecessary here because this thing's going to be adjustable. I can't just use a plain old M6 bolt. That's not going to work. I don't have a lathe, so I'm grabbing my cordless drill and heading over to the bench grinder. Having the work turn while the bench grinder does all the cutting makes a more uniform cut. I can't make it perfect like this, but it'll get the job done. After grinding down the bolt head, I use 320 and then 440 grit sandpaper to polish up the ball end of the bolt and screw this lifter back together. I'll use a lock nut to hold this thing at the correct height, but this method of construction permits me to make an adjustable solid lifter so they don't have to repeatedly disassemble and reassemble the valve train while guessing what size shims to use. I'll be able to use these on any 4G series head from now on. I'm doing the exact same thing with the next one that you just saw on the first one, but this time I'm going to weld the nut in place, making it one solid piece. I'm grinding a fresh surface on both parts so that the weld will stick, and I'm being careful where I set the welder's knobs this time. It's a much better fit and finish to weld the nut on, but aside from the welding, there's really nothing different about the concept of what I'm making. I'm just illustrating that there's more than one way to skin this cat. Sorry, Caboose. Probably the most difficult part is making a plunger with a head that's round and fits this rocker arm properly. And you saw the level of precision that I chose to employ to achieve that goal. I need 16 good rocker arms for this engine, and while going through the set I pulled out of the Hyundai, I found several that had been damaged by trash in the oil supply. It left grooves and indentations on the roller bearings that I don't want etched into the surface of my freshly polished camshafts, and several of them had worn pads where they contacted the valves. Once upon a time, I had the foresight to harvest a full set of rocker arms from a junkyard car, and I'm really glad I did that because a full set of these things are very expensive. Also, one of the Hyundai rules is that all the parts used in its construction absolutely must be used. I covered the cleaning and inspection process in another video, so I'm not going to go into a lot of detail here about it. I just wanted to point out that you should ensure that there's no wear or damage on the rocker arms, and no imperfections or grittiness in any of the roller bearings. You need this sorted out before we delve into the next stages, because we're about to start assembling the cylinder head. So now I've got my lifters, a couple sets of rocker arms, and some 3G lifters that I've been soaking in oil for years. My crankshaft degree wheel adapter, the lifter tool, the top dead center locator tool that some people have figured out that they should be using, or if you want to use the cheap and old school and spend more time finding top dead center, you can use the standard run-of-the-mill Chevy small block piston stopper, a pad of paper, and a pencil. You'll need dial indicators to measure valve train lift, and if you discover that the cams are out of phase, you'll need adjustable cam gears in order to correct them. The degree wheel, cams, caps, bolts, basically everything necessary to assemble a head and degree the cams are here. I just need to do a final cleaning, and we'll get this Hyundai back in business again. You should have 24 clean cam cap bolts, and thank you, Scott, for doing that for me and for giving my wire wheel a blood transfusion in the process. Everything else is laid out here and ready to go. So I'm going to wipe everything down with denatured alcohol to remove any remaining foreign material. This is your last chance to do this to ensure it's all gone. Make sure that not only the cam journals are clean, but the oil holes for all of the journals and the hydraulic lash adjusters are cleaned out as well. Make sure any gasket mating surfaces, bolt holes, and the tips of all the valves are clean. Because once you squirt assembly lube or install oiled parts, any foreign material left in here becomes part of your build. It gets trapped in that oil. Thoroughly clean and inspect every single part. Next, you want to purge all the oil out of your lifters so that they're deflated and squishy. If you leave oil beneath the check valves so that they sit in their rigid inflated state, it's possible that they'll hold the valves open during the testing that follows after we assemble the head, and it'll give you bad readings or even potentially damage the valve train if your engine is built with extremely tight piston to valve clearances. I explained how this tool we made works already, and this right here is when it needs to be used. Once you have them all drained and squishy, insert them into their bores in the cylinder head and leave the front two HLAs out on cylinder number 1. Next, we install our cleaned up rocker arms. Lubricate the rollers while rotating them to work the assembly lube deep into their roller bearings, and apply lube in the cups and on the pads where the ends contact the valve train. Soaking them would be ideal, but since I just cleaned them, this will have to do for now. We're going to install our 2 rigid test lifters into these bores to eliminate any deflection in the valve train while we're taking our measurements. I said I was going to use lock nuts and my intentions were good. I tried it, but it didn't work out as well as I'd planned. The lock nuts were actually too tall and I ended up removing them before doing my tests. But hey, I tried. Maybe I'll make thinner lock nuts later. I'm done making a mess for now. Goop these things up real good with assembly lube. Give the cam caps all a thorough cleaning with denatured alcohol and coffee filters to ensure that they're all spotlessly clean. It's time to install the camshafts. Yes, indeed, used camshafts, just like I said. This is the intake cam. It's a 264 duration HKS camshaft that's a very popular and proven choice in the street strip built DSMs. This Hyundai just keeps getting sleepier and sleepier thanks to my used parts bin. Thoroughly lube the journals and set these things in place. Either use 40 weight motor oil or your favorite assembly lube. Run all of your cam cap bolts down by hand so that you can feel if you have any fastener problems. I like to do a 3-step process on bolts like these. Step 1 is hand tight, step 2 is half the torque load, and step 3 is the final torque load. I follow the OE specification for tightening order and torque loads so that the spring load is distributed evenly across the camshaft as the bolts draw it closer. The torque specification for these 12mm bolts is 14 pounds. As an additional and unnecessary precaution for as far as this procedure is concerned, I'm also using a wrench that gives me feedback in case I over-torque a bolt. So now with the cams installed, I just need to adjust these lifters for zero lash. This just means that I set them so that there's no gap between the roller rocker and the camshaft when the valve is closed. Negative lash would mean that the valve is slightly open, and that's an acceptable method only if you're just measuring your opening and closing events. With the test springs installed, it's easy to remove and reinstall the rocker arms while making adjustments to these test lifters. The camera ran out of tape when I removed those lock nuts, but I didn't need to show you that, so I didn't. Now it's time to install the cam gears. Make sure the dowel pins are on top. These purple cam gears were junkyard finds. The original fasteners were shot, so these were drilled, re-tapped, and refitted with some steel cap screws and some modified washers. That's the story that was given to me, and looking at them I have no reason to believe any differently. They work perfectly though. The torque required for the cam gear bolts is 55 pounds. On the previous build, the cams needed several degrees of adjustment so that the car would idle properly. But for our purposes in this video, we're just going to set them to 0 so we can get a good idea of what our valve timing baseline is. There are many variables affected by parts selection and machining which play into your valve timing events. No two engines will be exactly the same. Even with aftermarket parts, the measurements frequently don't match up with the spec sheet. But when the planets align and they meet within a degree of rotation, that's awesome. A couple of degrees out, you can get by. If timing events are out of spec so far that you need to make adjustments, or if your valve clearance is too tight, then you need adjustable cam gears to correct it. I'm going to remove the crank pulley so that we can put our timing belt on. I'm not going through the complete timing procedure here. The timing tensioner is still set to where it was on the old belt, and the old belt wasn't that old, so we're going to rely on that setting. I'm just going to compress the tensioner and slip the belt on for now. I'm using a new Mitsubishi belt. The trick is to install the belt over all of the cam gears except for the tensioner pulley. Right before you slip the belt over the tensioner pulley, rotate your exhaust cam clockwise one tooth. Then slip the belt over the tensioner pulley to lock all of the other gear teeth in place. Because I compressed the tensioner to install the belt, I need to put the pin back in it before I take the timing tensioner tool out. The factory service manual says that you need to turn the engine over 2 times clockwise, wait 15 minutes, check the pin, and then pull it if it spins freely. However, the factory service manual doesn't tell you why this is necessary, but it most certainly is necessary. When you crank the engine over, oil will flow past the check valves and the lifters and inflate them. While they're inflated, they exert a greater spring load on the cam lobes of any of the open valves, and this puts pressure on the camshafts. It takes about 15 minutes for that pressure to bleed down. So until the cam gears settle, your timing marks don't mean anything, and the pin and the tensioner will remain tight as long as these forces exist. By 15 minutes they shouldn't exist anymore, or else you did something wrong setting your belt tension. Check all your timing marks, and if those are straight, and if your belt tension is correct, then the pin turns freely, meaning it's time to pull it. All the work we've done up to this point was just to perform one simple series of tests, and now that the engine is timed, we can proceed with those tests. This is the $20 11-inch Summit degree wheel, which I showed you earlier. Make sure you pick the right collet for your center bolt. I test fit the collet with the wrong bolt here, but I caught it and fixed it later. That's the nice thing about this channel. I get to relive my mistakes in the edits and go fix problems. Yay. Just like in the previous video, I'm using a copper wire pulled from a section of Romex for the degree wheel pointer. You may have caught a scene just a minute ago with the original top dead center pointer I made, still lining up with the crank pulley mark. I've lined that one back up, and I'm setting this degree wheel pointer to 0 based off of that mark. Now I'm going to check to make sure none of it got disturbed while I was messing around up here. I'm using this top dead center finder rather than a piston stopper because I find it easier. This works just as well with a dial gauge. You thread it through the spark plug well just the same as you would with a piston stopper, and then you set up your dial indicator centered vertically off of its anvil. You measure the peak of the swing at top dead center, and that's true top dead center. All I'm doing is matching my pointer to 0 when I find that mark, and apparently my old mark was right from the last video because I didn't have to change a thing. Top dead center locator. That's what this thing does. There's lots of other videos that demonstrate this piston stopper method, but if that's what you want to do, that's what you can do. Let's move on. One of the problems with dial indicators is how short the indicator plunger is. On an overhead valve engine, the retainers are so deep down inside the cylinder head that you need a longer plunger. Fortunately, this little thing unscrews, revealing some tiny little threads that can accept extensions. I don't have any of those extensions for this gauge. Heck, I don't even have that particular tap, but I can improvise. I've got this 1/8 inch 4043 aluminum TIG rod. I cut 5 inches off of it, and I'm going to cut the smallest threads I've got a die for. That happens to be M3, which is very close to what this is. The fact that this is aluminum means it won't strip out the steel shaft on my dial indicator. I've seen others recommend using a coat hanger, but I feel better about using this material. When you're finished cutting threads, round and polish the other end of this tool to avoid scratching the parts that you're measuring off of. Now let's get set up to take some measurements and see what we've got. We're going to start on the intake cam. I like to use this cast iron timing mount that you get with the first generation cars to anchor my magnetic base to. Do whatever's necessary that allows you to get a rigid straight shot at the valve train. You'll want it perfectly in line with the valve stem and your rocker is set to 0 lash. Any variation from this and your lift numbers will be wrong. It's a tight fit where you need to set up your dial indicator because you don't want to interfere with the cam lobes as it rotates, and you don't want the extension to touch the camshaft itself because either condition will throw your readings off. You get one little corner of the retainer where there's enough clearance, where you can still easily keep the indicator parallel to the valve's travel as it's compressed. Rotate the crankshaft until the gauge stops moving while that valve is closed. Zero your dial gauge at that point. My camshaft specifications for valve opening and closing events are measured at 1 mm on the spec sheet, which is 0.040 inches. Really, it's 0.039 something something something. Once you've got that dialed in on your indicator, mark your degree wheel where the pointer lines up. My intake valve is opening at 6.5 degrees before top dead center, with the cam gear set at 0 degrees and the valve lift at 40 thousandths. Next, rotate the camshaft until you find the point where the valve is at its maximum lift. Pinpoint that degree mark and make a mark on your degree wheel to indicate the intake lobe center line. This measurement isn't as critical as the open and closing events for what we're doing, but it lets us check our work once we're finished and verify the accuracy of the grind. Now turn the crank clockwise again until you reach 40 thousandths as the valve closes. Mark your degree wheel for this closing event. It looks like we've got 25 degrees after bottom dead center. The open and closing events should be compared to your cam card, which I don't have. Thanks to the internets and a kind gentleman named An Oldsman who posted them in English back in 2002, I can reference what the community knows about them. The first thing An Oldsman point out is that the translated specifications are incorrect concerning their center lines, and I've verified this. They are indeed wrong. If the intake valve is supposed to open at 2 degrees before top dead center and it closes at 28 degrees, if you run these events through a centerline calculation, your installed centerline should be 103 degrees, not 105. We're not using the centerline method for degreeing camshafts today. According to my measurements, at 6.5 degrees, I'm about 4 degrees advanced because my valve timing events are occurring earlier than they should according to their spec. So in order to match those opening and closing specifications at 1 mm, I need to retard my intake cam by 4 degrees. You'll notice in large print on the cam gear that each mark represents 2 degrees on the crankshaft. So we would need to retard the camshaft 2 degrees in order to move the crank 4 degrees. So we'll loosen the cam gear bolts, grab the camshaft by the hex and rotate it 2 degrees. When you lock your fasteners down, some cam gears tend to drift slightly, so you may have to do this a few times before you get your measurements perfect. Really, you just need to be within a degree of spec. You may prefer to build a degree or two into your final numbers depending on how you'll use the engine or how you want it to behave, but within a degree of spec is the goal you want to shoot for starters. We've got 2 degrees before top dead center. That's spot on. It might be 2.2, but I'm happy with that. My center line measures on the fat side of 100 degrees after top dead center. My intake valve closing is happening almost on 29 degrees after bottom dead center. The camera angle is just a bit to the right, making that look like a 29, but really it's on the fat side of 28. That's within 1 degree of spec. If I felt like removing these studs, then I could put a magnetic base here. But I don't feel like removing any of these studs, so I'm clamping up with the flex stand for the exhaust measurements. Honestly, it's the first time I've ever used this vice grip mount. Not bad, not bad. You orient the probe exactly the same way on the exhaust side as you did on the intake valve retainer. Find your closed measurement, zero the gauge, and turn until you find 40 thousandths. Here I find 26 degrees before bottom dead center as the exhaust valve opening event. Turn the crank until you achieve maximum lift. I've got it set here, looks like the 101 degree mark. Mark it and turn it to 40 thousandths to get your closing events. It's on the fat side of 8 degrees after top dead center where it closes. Looking at our specs again, we find that the exhaust valve opening event should occur at 36 degrees before bottom dead center. I've got 26 degrees, that's 10 degrees retarded. The same thing goes for my closed measurement of 8 degrees because 10 degrees later on the other side of 0, it's 2 degrees. Providing that the opening and closing events are correct on HKS's spec sheet, then I need to advance the exhaust cam 10 degrees in order to bring it back to spec. Do you think that has anything to do with how the cylinder head deck was milled crooked on one of the many times that it was decked? Well, do you? Maybe? Maybe there's some differences between using an Elantra head on a non-turbo Galant block, maybe? Maybe the locations where the keyway on the crank or the dowel pins on the cams are centered? It doesn't matter. Every engine is different. You can't just set your valve timing up like some other guy did it and expect it to be even close to where yours needs to be. The only way to know your engine is timed correctly is to do these inspections. Everything short of that is guesswork. If I told you that this is as complicated as this process gets, or that I'm done, I'd be a damn liar. All we did is dial in the cams to the manufacturer's spec, and that's really the easy part. Getting the most out of your camshafts involves dozens of other factors that I can't possibly cover in a half-hour video. There's only one step left for this process that you should do whenever finalizing your valve timing measurements, and that's to make sure that true top dead center still lines up on 0. It's just like checking your math. You do this to make sure the degree wheel didn't accidentally get moved somewhere along the way. If it moved, you have to do it all over again. It's dead on where HKS said it should be. I've got the exhaust cam 10 degrees advanced, the intake cam about 4.5 degrees retarded. You can see that there's no way that my engine would have benefited from these camshafts without adjustable cam gears because of how far the timing was off in my particular engine. And that's the point I wanted to make for everyone out there considering installing a set of aftermarket cams. Camshafts are not upgrades all by themselves. They're just behavior modifiers. You can't put an enormous dog in your one-bedroom efficiency apartment and expect him never to poop on your rug. You probably want to start with a dog that's the appropriate size for your house, but you still have to train him not to poop on the rug. Installing camshafts is a lot like that. In this video, what I've demonstrated is how to make the tools necessary to train that dog, and how to make him sit up straight. We're not out of the poop yet. In the next video, we'll cover valve clearance and the best ways to make that dog speak and roll over before moving on to more advanced topics, like bang and sick 'em. Please feel free to click any combination of the like, share, or favorite buttons if you learned something here, and I'll be back with another episode very soon. I thank every last one of you for your curiosity, time, and attention, and for clicking in on another episode here on Jafromobile. Until next time, stay tubed.
Sit. Speak. 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 Speak.